Okay, so we will continue covering classification methods. So in our last lecture, we saw some classification methods. We saw logistic regression. We saw the Bayes classifier and the naive Bayes classifier. And so today we'll take a look at a couple more classifiers. We have k-nearest neighbors, and then we'll also look at support vector machines. Okay. So with k-nearest neighbors, what we are doing is we are going to look at each observation, and we will look for a test case. Okay, we look at what we call the nearest neighbors of this test case, and based on that, we try to make our prediction. Okay, this is what we call a instance-based learning method. It's also non-parametric. Okay, it is with different, like the Bayes classifier, you needed to have some kind of model for generating the data. So we said our data, with the marbles, we said our data is coming from this Bernoulli distribution or binomial distribution where the marbles are being selected, independently and randomly. In the mixture of Gaussians, we said our values are coming from a normal distribution. So those are parametric methods. Here with k-nearest neighbors, we don't care what system is generating our values. We just say, oh, these are the values. Okay, so it's non-parametric. We're not going to try to figure out what is the distribution behind our values. Okay, the instance-based part is it's going to be based on the values that appear in your data and the value of your test case. Okay, and so this it just stores all of the training data set. And so one of the biggest disadvantages of KNN is that if you have a big data set, a big training data set, the KNN model is very slow and cumbersome. Okay, and the way it's going to classify a new observation is it figures out the k nearest points in the training set, usually by Euclidean distance, and then looking at the nearest points, they have, you do like majority voting, and whichever class is most common among the nearest neighbors, that is how it's going to classify your new test case. Okay, so the process goes like this. You have to, number one, compute the distances from your test point to every single data point in the training set. Okay, and again, this step can be very, very computationally expensive, especially if you have a big data set. Right, and then once you have all of those distances, you sort them least to greatest, and you pick the k nearest points, the k observations with the shortest distances, and then you use majority voting among the k neighbors. So we need some kind of distance metric. We frequently use Euclidean distance, but you can use other measures of distance. So there's so Euclidean distance is kind of the L2 norm of the difference vector, but you can also use like Manhattan distance, which would be the L1 norm. I don't know, there's other cosine similarity. There's different distance metrics for your differences there. If you have a categorical variable, okay, that's it doesn't work so great for k-nearest neighbors. Okay, so it's easy to measure distance when you're on the number line, right? The distance from 0.7 to 0.12, that's a 5-unit distance. From 10 to 25, that's a 15-unit difference. Okay, if you have categorical features, what's the difference? What's the distance between red and yellow? Okay, what's the distance between red and blue? It's a lot harder to try to quantify. Now you can try to do dummy encoding and code variables as ones and zeros, but then how far apart is the 0 and 1, right? That's a is it like if you have handedness, right-handed versus left-handed, and then let's say you have gender on another thing, right? If you just encode these as dummy variables, is the difference in handedness equivalent in magnitude as the difference in gender and things like that? That's a tough question, right? And so how do you meaningfully interpret distance when you don't have numeric values? Okay. Because you are using distance, though, all of your features, you want to scale them to a similar range, generally speaking. Okay, so again, kind of like the same kind of issues with lasso, where you have different units, can lead to kind of different issues here. When you have different numeric variables, you probably want to scale them so they're on similar scales. So standardizing them so they have mean 0, standard deviation 1, or min-max scaling, so the min is 0 and the max is 1, or something like that. Is what we can do. Okay. One feature can have a much larger numeric range than others. So, for example, if you're talking about weight, it's not uncommon for two people in your data set to have a difference of, say, 100 pounds between, one person and another person, right? Whereas if you're talking about height and you're using inches, you're not going to have 100-inch difference between your shortest and tallest person. It's going to be maybe 20 inches. I don't know. Okay. So you're going to have, right. So scaling, important. Okay. Unless the magnitude is important and you don't want to scale. I don't know. Like a lot of times when you're dealing with money, you might not want to scale money if everything is in the, but then that's kind of assuming all of your variables are money. And so that's kind of the thing, right? Because like with money, it's like, okay, I don't know, the parts on the wheels, maybe it goes from $100 to $110. Okay, your cheapest wheel is $100 and your most expensive is $110, and then some other part, the cheapest might be like $100 and the most expensive is $1,000. You don't want to kind of, and if we're talking about like total costs and stuff, you don't want to say the difference between 100 and 110 is the same as the 100 to 1,000 or something for money, but anyway, yeah. Question.
Could you use like different types of scaling for different variables?
Yeah, probably. That seems like you have to. You'll want to think about it some more. Yeah. But yeah. Generally, we don't think too hard. but yes, absolutely. If you say, wait, it doesn't make sense to scale this variable in the same way as the others, then yeah, use your kind of reasoning and intuition there. Okay. When you do k nearest neighbors, you got to pick the k, which is how many neighbors do I allow to influence, the vote or the classification, right? So do we just use the one nearest neighbor? Okay. If you do that, then you have a model that's highly flexible, captures any of the kind of local patterns, any like small differences here and there very closely, but you're going to overfit. Okay. High risk of overfitting, high variance. It's going to be really subject to just, if one random individual pops up over here or something, you're going to have kind of a lot of noise. Okay. On the other hand, large K, the extreme would be k is equal to the size of your training set. Okay, if your k is equal to the size of the training set, then it's just going to be majority voting for everybody. Okay, so the majority class, if the majority class is red, then everybody will get classified as red. Okay, in your test case. So probably not ideal, but that tends to the other side of high bias and low variance. Okay, and you can use cross-validation to try to figure out the balance in terms of, do we want a small or large k. As far as sometimes you can end up with a tie. So when you take your k nearest neighbors and they all vote, occasionally you end up with a tie. You can avoid this if you have only two classes. You just make sure there's an odd number of k, right? And that's going to avoid running into ties. But as soon as you have more than two classes, then it's possible where you have a tie. And there's no hard rule as far as like how we should resolve ties. Okay, the safest is to just designate it as unclassified, but that might be the least satisfying. Okay, and then so you can select randomly among the top tied groups. You can also have weighted voting, and you say each vote is, the vote neighbors that are closer, their votes count more, and the neighbors that are farther away, those votes count less. And then you'll have this numeric scaling, and you're less likely to run into a tie that way. You can also just do the one nearest neighbor, and then among the top tied groups, you can select the group with the closest neighbor, which is not necessarily the same as the one nearest neighbor. Okay. So these are all different ways as far as resolving ties. Okay, but anyway, KNN is implemented in R using just KNN, but yeah. I guess I should talk about computational complexity. So I would say KNN is still popular, but when your data set gets big, then it is discouraged. Okay. Because of this first step right here. You have to compute the distance from your test case to every single point in the training data set. And when we look at our examples of this, you're going to be like, why would we bother computing the distances? Because I can just visually see these points are the nearest ones and these ones are far away. Okay, in 2D, yes, that's the case. But if you have high dimensional data, all right, now we're no longer really able to visualize it, and then the idea of which ones are the closest is a lot harder to identify. And then so you end up having to compute the distance to every single other data set. Now, so for very large data sets, usage of KNN is discouraged. There's strategies for handling this. If you still want to use KNN, you can kind of randomly downsample so that you're not calculating distances to the entire data set, but just maybe a smaller subset that you're hoping is representative of the entire data set. That's possible. But anyway, if you're familiar with big O notation, you can see that a lot of these, as n gets bigger, these things get bigger. So calculating the distance, that's O of n, and then basically sorting the distance is going to be O of n log n. So these all get big, right? Oh, and if you have number of dimensions being really big, yeah, this operation can be quite expensive. Okay. There are other things. There's the KD tree, and that can be used to kind of speed up neighbor searches. I don't know if KD trees are even that popular anymore, but that's that. Yeah, I think K nearest neighbors is still kind of a popular method, but I don't know. As far as like imputation. I think it's a popular method for figuring out like missing values. So a lot of times, like your final model, I want to say these days, the final model is almost always like a neural network, maybe a boosting trees. Okay, but a lot of times it's like a neural network, but then for your neural networks, you need to have complete data most of the time. And so what do you do if you have missing data? You often impute your missing data values by using k-nearest neighbors on the features that aren't missing. So you say, okay, well, I'm missing, waist size, right? You're taking different dimensions. And so we say, okay, well, looking at the other features, height and weight and head circumference or whatever, we'll look at who's similar, and based on that, we're going to figure out waist size. So I guess that's a regression case. And you can also use k-nearest neighbors for regression by just kind of taking the average of the numeric values rather than just majority voting. Okay. Anyway, as far as KNN and its classification, it's generally considered to be a hard classifier because it makes decisions by assigning a class label that is most frequently that appears most frequently among the k-nearest neighbors. Okay, you can kind of extend this to get what we might consider like pseudo probabilities. These are not real probabilities. Okay, but it's just like, okay, if we look at the 5 nearest neighbors and 3 of them are class A and 2 of them are class B, then we might say, okay, this test case, we're going to assign a probability of 60% to class A by looking at the 5 nearest neighbors and getting kind of this fake-ish pseudo probability, okay? So again, they're not true probabilities. There's no underlying model. Okay, we're just looking at like, okay, these are the 5 people that we think are most similar to you, and of the 5 people, this is kind of the general consensus, and so this is what we infer to you, right? So this is, again, it's non-parametric. There's no probability model there, okay? Okay, so these are the other distance metrics, other things that we can consider. So you have Manhattan distance, basically some of the absolute values. Chebyshev distance is the absolute difference between any coordinate of the 2 points, the maximum absolute distance. So you look at like the difference in x1 and the difference in x2, and it's just the max of those things. It's a little bit of a weird thing. And then cosine similarity looks at kind of the angles between the vectors, okay? All right, these are the advantages of KNN. It's very simple. You don't have to worry about any kind of underlying data or distributions, and there's no training phase, okay? It's just, here's all the data, so that's it, okay? But the disadvantage is, again, very computationally expensive for large training data sets. Large data sets will take a lot of space and memory. There's no rule to learn. It's just kind of instance-based. Here's the test case. What do we think it is? But there's no like, okay, after we learned all of this, anytime x is greater than 7, we're going to class it. No, you don't get any kind of rules based on that, okay? And then what else? Okay, yeah. High dimensional data is always hard. I mean, that's going to be the case for almost everything anyway. Okay, choosing your K, not always straightforward. We like to use cross-validation, probably our best strategy for handling how to pick our K. It is sensitive to outliers, just because your distance metrics are skewed by extreme points. So you might want to consider outliers. And then if you have missing values, then KNN falls apart. Okay. And then if you have something that's very imbalanced, okay, KNN, because it's using majority voting, it might always just predict the majority. All right. So here, to just make up some data points, I'm just going to generate two-dimensional data, and this is what we have. Okay, so I've got some red dots, I've got some blue dots, and we'll use this to try to figure out, like, to guess things. Okay, and so let's say I want to put a test case right here. And again, what the first step is to measure the distance from this test case to every single other point in your data set. Now, again, it might feel silly in 2 dimensions to do this because our eyes can easily judge and say, okay, points in this vicinity are going to be the closest, so maybe I only have to measure the distance for a few of these points. But again, in high dimensions, it's not so obvious which points are your nearest neighbors. Okay, but anyway, if you do K is your one nearest neighbor, this is my one nearest neighbor, and I've drawn a circle to kind of around, from the test case. So this has this radius, and you can see that there's no point that's closer than this red dot, and so it's going to classify as red. With K equal to 3, these are the 3 nearest points. We have 2 red and 1 blue, so we would still classify it as red. If you have K equal to 5, though, with K equal to 5, now we have 3 blue and 2 red, and so with K equal to 5, this would get classified as blue, okay? And then with 7, these are our 7. This came really close, but is not. But anyway, we have 4 blue and 3 red. This gets classified as blue, and that's that. Okay, here's another test case. Over here, we look at our calculator distances. Okay, our 1 nearest neighbor, it's red. Our 3 nearest neighbors, we have 2 red and 1 blue, so it gets voted red. With our 5 nearest neighbors, we have 3 red and 2 blue, so still votes red. And here with 7, we have 4 red and 3 blue, so this one still votes red. Okay, and that's what we have there. Okay, all right. So here's just a bunch of code that I copied from Stack Exchange. In this, I took the same data set. So these are the same. If you look at these dots, like you look at where the red dots and the blue dots are, this is the same dots. And then what we have here, I don't know if you can see, there's like this tiny little grid of points, okay? And basically, I had the computer do K nearest neighbors, K equal to 1 for every single dot here, and then just color them. So you can see this dot right here, when we said, what's the 1 nearest neighbor, let's look at this dot. It said the 1 nearest neighbor is this dot, so it's going to get blue, okay? But then if you go over here, this dot, this tiny little dot, what's the 1 nearest neighbor? It's this red circle here, and so this gets classified as red. So this goes through, looks at our data set, or all of these different test points, and doing K nearest neighbors, K equal to 1. This is how it classifies it. And so we get kind of these regions that are shaded red and blue, separating our red and blue boundaries, okay? And that would be K equal to 1. If you do K equal to 3, our boundary shifts around a little bit, okay? And so, this point out here feels kind of like an outlier for red, and so it's still going to get, all of these dots just get classified as blue, okay? And here it is with K equal to 5, K equal to 7, whoops, okay. And so as we increase K, it's not that the boundary itself gets kind of smoother, but it's kind of like tending towards a simpler defined boundary that is less influenced by individual points, okay? Because now the classification is looking at the 7 nearest neighbor. So just one point that's kind of an outlier, or kind of feels not where it belongs, has less individual influence. Here's another data set with more dots, okay? And so here overall, the right-hand side is red. Overall, the left-hand side is more blue, but we do have some kind of mixing, right? There's a kind of a blue dot here and here. There's a few red dots over here. So how does this get classified? Okay, if I do the same kind of boundary drawing here with k equal to 1, you can see you get all of these enclaves and exclaves, these little islands of kind of each, little territories carved out by either red or blue here, okay? And so these dots out here kind of have managed to kind of carve out their thing. And so this is, we would say this is going to be very subject to, any kind of noise, any kind of like random things, okay? As I increase my k, right, these individual dots that are kind of outliers have a little bit less direct influence, right? So these two red dots manage to kind of form their own little circle here, or form their own little island, but these ones out here, not as much, okay? You do get some kind of slightly weird artifacts, like here's like this little pocket that gets categorized as blue just because there's like 3 blue neighbors nearby and stuff, okay? Here it is with k equal to 5, okay? And you can see as I increase my k, the boundary tends to be a little bit, I don't know, simpler might be the right word. I'm not sure what the right word is, but yeah, we tend towards lower variance, and if you max out k too much, then you're going to have high bias, okay? So here, between k equal to 7 and k equal to 9, not a huge difference. And here it is at k equal to 15, k equal to 21. Now we're kind of it's kind of stabling out, okay? And at k equal to 31, so we have a very high, and then now we're kind of just getting almost just a straight line down the middle that just says the right-hand side is red and the left-hand side is blue, okay? But probably somewhere in between here, and we'd probably use cross-validation using different values of k. We would subsample to 80%, 20% splits or something like that. Use cross-validation, see how it performs, and try to determine it that way, okay? So what do we have? Smaller values of k can lead to overfitting. Larger values tend to oversmooth the boundaries. Okay, I think that's about it. And then yes, k and n can be extended for regression. Same thing, distance calculation, find your neighbors, your nearest neighbors, and then as far as making a prediction, rather than taking a majority vote of like, is it red or blue, you just take the average of the k nearest neighbors. So if you're doing k equal to 5, you take your 5 nearest neighbors and you take their average. You might also do a weighted average, and you'll say, okay, the ones that have the shortest distance, they're weighted more heavily, and then the ones that have farther distance, they're weighted less heavily. You can pick different kind of weighting functions to say this is how we do that. So k and n can be extended for regression there. Okay, let's see. Let me give you your first view quiz answer, which is the letter D. D as in dog. D as in dog. Okay, so that's that for k nearest neighbors classification method. All right, and then let's take a look at support vector machines. Support vector machines, like the name sounds so fancy. It's just, can we draw a line to split it? Okay. So this is another classification method. It's supervised learning. Supervised learning just means we have the answers. Okay. And what we're looking for is we're trying to find a boundary that separates the points belonging to different classes, okay? And support vector machines, really, we only have two classes, okay? So k-nearest neighbors can technically work for more than two classes. Like if you have three classes, you can still do like majority voting. Support vector machines, we can really only kind of separate out two classes. So if you have something more complicated, you've got to kind of turn everything into, this class versus not. So if you have like red, yellow, and blue, you're going to have to kind of split up your data into red versus not red, and you'll have you'll get your boundary drawn that way. Okay, and then you have to do yellow versus not yellow, and you get a boundary drawn that way, and then you do blue versus not blue, and you have a boundary drawn that way. So the simplest version of support vector machines is the maximum margin linear SVM, which is way too many words to just say draw a straight line that splits our data into two, okay? And that's only going to work for data that are linearly separable. And so if we have two-dimensional data, we're looking for a straight line. And if you have higher dimensional data, you're basically looking for a flat plane, okay? Or a flat hyperplane in extra high dimensions. But yeah, two-dimensional data, you're looking for, I guess, one-dimensional data, you're just looking for a boundary, okay? Greater than 5, less than 5. In two-dimensional data, you're looking for a line. In three-dimensional, it would be a plane, and then higher than that, you have a hyperplane, okay? And we want to separate the two classes from each other, where basically the distance from these hyperplanes is as wide as possible, okay? And so we'll start off with some data that is linearly separable, okay? And then from there we will say like, okay, what is the maximum margin boundary here, okay? So let's say this is our data here, and we want to kind of separate it. So we want to kind of pick some kind of line that can separate this, and the maximum margin basically means try to find something that's like really in the middle, so that distance to that line is maximum, right? So here, this would not be an optimal boundary, okay? This line down the middle does correctly classify everything on the right as blue and everything on the left as red, and I've got the right side, blue being blue pluses, and then red being red minuses. This is a correct boundary, correct classification, but the distance from the boundary to the nearest points is pretty small, okay? So the boundary is the line down the middle, and then we have what we call parallel hyperplanes, but basically just you have these parallel lines, and basically the width of the railroad track is pretty skinny, okay? But if you pick like, so what is this? One possible linear boundary that perfectly separates the two, but the boundary has a relatively narrow margin, and you can try other ones, right? You can try different angles here. And if you kind of go through, you'd say, oh, okay, you know what? This one produces a pretty wide margin. So here's the boundary. You look at the points that are closest to it. So we have these two that are on the line, on the parallel line, and this one's on it. And if you measure, this is the widest kind of possible margin, okay? And if I try picking other angles, you get smaller margins, right? So really, these somewhere around here, and then, but this one's the widest one, okay? So that one's the widest, and everything else is going to be thinner, okay? So the one we want to pick is the one with the widest margin there, okay? So that's what we're going to try to do, okay? Is we want to find that specific boundary, that linear hyperplane, that's going to maximize the margin between the two classes. And the margin is going to be defined as basically that width, the perpendicular distance from the decision boundary to the closest data points on either side. Because if you look at this, here's our decision boundary, and then we're looking at basically the margin goes up to the points that are closest to the boundary, and we're going to say, okay, how far is this distance, right? And basically this decision boundary is right in the middle between basically from here and from here to here. We got the same distance there, okay? So that's the margin. And so those points that are on the margin's edges, those are known as the support vectors, okay? Because once you have these 3 points, these are really the only 3 points that determine where this boundary is, okay? We could add or take away points over here. We can add or take away points over here. And as long as we're not putting a point inside this margin here, this boundary is going to remain unaffected. And I think, I didn't illustrate that, but so those are the only points that directly influence the position and orientation of the maximum margin boundary. If you were to move or remove any other data point, okay, as long as the support vectors remain the closest points to the boundary will not change, okay? So that's why we call them the support vectors. They support that boundary here. So, so here's our maximum margin linear support vector machine. Basically just here's the line that we draw, and our support vectors are these 3 circle points. And then this is the, I guess, twice our margin here, okay? Here's our non-optimal boundary, and this has a much smaller margin, okay? So how do we do this? How do we maximize this margin mathematically? Okay, we can come up with kind of a series of equations here, and this will get it into a form that we can ask the computer to then optimize. And so the computer is going to do something called quadratic programming, which is, it's an iterative method to find an optimum, okay? But the idea is we have, a bunch of kind of points where x is the location, so, x1 and x2, and then t is going to be the class. And we either have +1 or -1 for our 2 classes here. And so we want to figure out what this support vector location is, this maximum margin thing is. And what we want to do, all right, is we want to maximize that distance from the hyperplane to the nearest point from either group, okay? And so the hyperplane is going to be basically the set of points that satisfy this equation, okay? And W is some vector that's perpendicular to that boundary hyperplane. And so hyperplanes that are parallel to this are basically just one constant higher, one constant lower, okay? So you can have W transpose X minus B equal to 1 and W transpose X minus B equal to -1. And this will be kind of the parallel hyperplanes. These will define that parallel hyperplanes for either the positive side of the margin or the negative side of the margin, okay? Where the boundary is going to be in the middle, where this, W transpose X minus B is equal to 0, okay? So you have a W that defines kind of the direction, and then the set of all X that satisfy this, okay, will form the hyperplane. So, so just to kind of label everything, this line down the middle, so I don't know. For example, if W is equal to 1, 1, okay, then there's going to, and we want W transpose X plus B equal to 0. But let's just, like if I, so let's say, we'll say B is equal to 3, okay? What values of X? So basically I could put in X at, like 0, comma, negative 3, wait, plus 3, right? Yeah, okay. So if X, so one possible set that would satisfy this would be 0 and negative 3, right? Because W transpose X would be 1 times 0 plus 1 times negative 3 plus 3, or B is equal to 0, right? So that works. And then I could also, another X that would satisfy, if I put in 1 here, then I would need to have like a negative 4, okay? I could also have X equal to, say, negative 1 and 2, I think, right? So 1 times negative 1, am I doing this wrong? Plus, oh, negative 2, sorry. Wait, negative 1? Okay, anyway. So if we were to plot all of these things, 0 minus 3, that's one possible thing, okay? And then if I go out to 1 and I have minus 4, and I have negative 1 and negative 2, where is it? Right there, okay? You will see that this, we get kind of a, all of the points along this would form kind of like just different possible solutions of X that will satisfy this equation, right? And then we could have a parallel one where this thing is equal to 1, and then you can have another parallel line where it's equal to minus 1, right? So you can, so this is just kind of like one possible thing, and so you can locate all of these things. So over here we have, W transpose X plus B is equal to plus 1, W transpose X plus B is equal to negative 1. And so what we can do is we can take this vector, we have 2 points along that are located on opposite boundaries, right? So we have this point X, we'll call this one X1, is on this this boundary, and we'll have this one on this one. This purple vector is the W, okay? So if W is 1, 1, okay, it's pointing in this direction, and it is perpendicular to this, right? So we can dot this vector to or project it onto this vector to kind of get the distance there, okay? Or I could have picked this one, and if I dotted onto the same thing, we'd get the same thing, okay? So basically, if we say x1 and x2 be the closest points from the from opposite sides, okay, that vector x1 minus x2 joins those points, and with the way the boundary is defined, this is going to be the direction. W over the norm of W is going to be the direction there. And then if I take that, basically I dot that vector x1 minus x2 onto W. So another way I can do it is just W transpose x1 minus x2 divided by this norm to kind of basically make it the directional vector. And we can say, all right, this is going to be equal to the width of the margin, or double the width of the margin, right? So if the margin is just one side of these things, we're going to have, our margin is going to be double that. So, so this will be the length of our margin. And what we want to do is we want to maximize this quantity. All right, so if we say this is on one side x1 is on one side of the boundary where we're going to get positive 1, and x2 is on the other side of the boundary where we get negative 1, okay? You know, with a little bit of substitution, okay, I can say, all right, here I have W transpose X, W transpose times x1 minus x2. This, I can kind of distribute that. I get W transpose x1 minus W transpose x2. And then basically I can add a b and subtract a b to both sides. Okay, so here this side is going to be basically positive 1, and over here this is going to be negative 1. All right, and so this basically just becomes 2 over here, and so I have 2 gamma equal to 2 over the norm of W. So the width of our margin is basically going to be just the norm of this thing. Okay, 1 over the norm of W. And so what this effectively becomes is that maximizing this margin becomes equivalent to minimizing whatever this is. Okay, now we don't want to just, if we have to constrain it, okay, we can't just pick whatever W we want, okay. There is the constraint that with all of the observations, okay, it has to, this W has to be selected in such a way that everything gets classified correctly. That is, for all of the X values that are on the negative side, that when you do W transpose X minus B, on the negative side, it's going to be, you know, less or equal to -1. Okay, you know, basically all of the points over here will get classified correctly, and all of the points over here will get classified correctly. So the sign of the points are basically positive 1 and negative 1 over here, the classification there. And so we can kind of combine this greater than less than business into just one thing by saying take the sign of this, whether it's 1 or -1, and when you multiply it by this thing, it has to be greater than or equal to 1. So you have this constraint, okay, and it has to be true for all values of X. Okay, so you're going to have, you know, whatever data set you have this many constraints. Okay, so we want to minimize this, and this is the same as minimizing the sum of the squares. Okay, so if we minimize this, or if we minimize this, it's going to be equivalent to that, but we have the constraint that it's going to classify all of the points correctly. Okay, and so when you're trying to optimize something subject to constraint, you can use Lagrange multipliers. Okay, and so we're going to have a Lagrange multiplier for every constraint that this is subject to. Okay, so we're going to have a whole bunch of these Lagrange terms. Okay, basically one for every single observation, because every observation forms a constraint in that it has to be classified correctly. Okay, so basically we're going to try to find the W that minimizes basically this norm, right? So the norm W squared is equal to W transpose W, and it's the same thing as minimizing this. And then every constraint is we have basically a Lagrange term times this constraint, which has to be true. Okay, and we have one of these for every single observation. Okay, so all of our Lagrange terms, have to be greater than 0, and this applies for every single data point in a thing. Okay, and so this can be done. There's not a closed form solution, but it can be solved using quadratic programming. I'm not familiar with quadratic programming, but apparently it can be done with an iterative search on our computer, and it will find the solution there. Okay, and so once you have this support vector determined, here I've just just illustrated, like here I added some additional points, I've subtracted some points, and the margin isn't going to change locations. Okay, so that would be the maximum margin linear classifier. So we want to do this, we want to minimize this thing. And when we do this, at the minimum, the derivative of this function with respect to w and b is going to be equal to 0. So doing this is basically kind of following this through and getting it into a form that we can kind of throw into quadratic programming. Okay, so we have this, we're optimizing this subject to these constraints. We take the derivative of this and set it equal to 0. So when you take the derivative with respect to w, or the gradient with respect to w, you get all of this. You can solve for w, and you have this. You can take the gradient with respect to b, okay? And you get all of these things. And all right, this is just a big mess of a page of all of this stuff. Don't worry about it, okay? Basically, this is in some, this is an inner product here between, basically we're looking at every combination, okay? Every value of x gets dotted with every other value of x, okay? Just because as we're kind of searching for this, we don't know which ones are going to be the support vectors. So anyway, it kind of goes through all of these things, and effectively, you know, via quadratic programming, it's going to figure this out, okay? And so as far as this optimization problem goes, it really just comes down to figuring out which values of x are the ones that are kind of relevant to it, okay? And those x's will have values of alpha, and then all of the other x's, basically their values of associated values of alpha are basically 0. They don't influence the support vector, okay? Or they don't influence the boundary. So the x's that do belong on the support vector, they're going to be part of this solution. Their values of alpha will be non-zero. And then all of the other ones will have alphas of 0 that don't really matter, okay? And then so when you identify those x's that do matter, okay, those are going to be the x's that define the that boundary w, okay, the vector that defines the boundary. Okay, so the support vectors will have values of alpha that are not 0, while everything else will have alphas equal to 0. And you know, basically whether x is on one side or the other side, that will determine the sign of it being positive or negative, and that's going to ultimately determine where our boundary is drawn, our w, okay? And so this letter alpha, okay, we can think of it as kind of how much influence a particular value in the training data has on defining w, okay? And w is really a matter of figuring out what these values of alpha are for each of the different values in x, okay? So that's our maximum margin classifier, and we can start to relax some of our constraints, okay? And so one way to relax this is by having what we call a soft margin, okay? And so we said this maximum margin classifier, when we defined it, we said all of these points over here have to be on the correct side of the boundary, okay? And so basically t times this has to be greater than or equal to 1, okay? But what we can do is we can kind of relax this and say, you know what, that the distance to the point from the boundary, we can allow it to be less than 1, okay? It can be 1 minus a small number, maybe epsilon is 0.3, okay? And so now we can say the distance to the boundary is only 0.7, okay? You could even have epsilon be greater than 1, and that means the point is going to end up on the wrong side of the boundary, okay? So now, because if you imagine you have an x and it's on the wrong side of the boundary, and you do W transpose X on this thing is now going to be the wrong sign, right? It'll be times T, it'll be actually less than 0, okay? So now we're talking about possibly having, a plus on the wrong side of the boundary. And that's what the soft margin says, okay? So, when you say, well, that feels like we're going to just end up with everything, all over. What is this? What should this be? Okay, so basically, we have all of this. Okay, the same kind of problem, but now we're going to kind of put an upper limit on what this alpha can be. So alpha is kind of like how much influence a single point can have, and we're going to kind of place an upper limit and say, this one observation, as far as, remember what W is, okay, we're going to put kind of an upper limit. So, if a particular observation has a lot of influence on what W is, this value might be a really big number, okay? And what we might say is that, you know what, we're going to kind of put a limit on how big any one value could be, because when you do this, there might be several observations that influence what W is, okay? And so that's what we have. That's going to be our soft margin. Okay, so anyway, this is the problem. It's still a quadratic programming optimization problem, and having our optimization problem in this form allows us to kind of do some silly things, like use kernel functions. Okay, so kernel is one of those weird words that just kind of appear in a bunch of different places, and they mean different things, okay? Here, a kernel is going to be a function that we can apply to a dot product, and it's going to be, it's going to symbolize that the result of this thing is basically a dot product of kind of like, we're going to apply a transformation function to our coordinates, and then take the resulting dot product. So this is kind of the original optimization problem, and here we're going to do basically the same thing, and we're just replacing this part, this X transpose X, okay? And again, we're calculating this for every kind of pair of points. So if you have 20 points, you're going to do basically find 400 of these things, right? All 20 right, for M and all 20 for N, okay? And we have to figure out like what our appropriate alphas are. So anyway, this goes there, and we're going to just replace it with this kernel function K, okay? And what this is going to be is it's basically the inner product or the dot product of these vectors after we apply some kind of phi transformation function. Okay, so we're going to apply some kind of function phi to it, and this is going to transform our vector into a different vector, and then we take the inner product. So let me just kind of illustrate with an example. So one example is you could have a vector x1 and x2, a two-dimensional vector, and then we're going to apply this phi transformation function, which basically just takes this and creates a third coordinate, okay, which is going to be x1 squared plus x2 squared. So this two-dimensional vector, which is just x1, x2, will become a three-dimensional vector of x1, x2, and x1 squared plus x2 squared. So if you have the vector 1, 1, when you plug it into here, it becomes 1, 1, and then 2, because you have 1 squared plus 1 squared. So 1, 1 becomes 1, 1, 2. So it goes from 2D to 3D. And then the vector 5, 1, okay, the third coordinate is going to be 5 squared plus 1 squared, so 26. So 5, 1 becomes 5, 1, 26. And so our kernel function is going to say, all right, take xn and xm. Xn is 1, 1. Xm is 5, 1. Apply these transformation functions, 1, 1, 2, and you'll get 1, 1, 2 and 5, 1, 26. And then take basically the dot product between them. So you're going to do 1 times 5 plus 1 times 1 plus 2 times 26. So you get 5 plus 1 plus 52, 2 times 26. Okay, and so 5 plus 1 plus 52 adds up to 58. So, okay, so that's the kernel function. Now it feels like, okay, well, why did we bother with that? Well, yes, you can apply the transformation and get this result of 58. There's also usually an equivalent kernel function, okay, that just gives you the result directly. Okay, so we can just say, if this is the transformation, I can transform it into 3D and then take the dot product, or I can just get this result directly, and we can just do x transpose x, take xm transpose xn, and then do xm norm squared times xn norm squared. So if we do that with 1, 1, and 5, 1, okay, so when we did the transformations, we got 58. But if I just say, all right, let's just do xm transpose xn, I get 1, 1 times 5, 1, okay, and so this is going to give me 1 times 5 plus 1 times 1, and that's going to give me 6, okay, and then I do the norm of this squared, okay, so that's going to be 1 squared times 1 squared, so 2, and then the norm of this, so 5 squared plus 1 squared, okay, so I get 26, and I get the same result, okay, this is going to be 2 times 26, and over here I get 6, so anyway, this also adds up to 58, okay, and so by doing this, now I have, you know, an equivalent, we have an equivalent thing here, okay? So what was the point of this, right? The point of this is that we might be in a situation where when we look at our two-dimensional vectors here and here, and we're trying to like find the distance between these two-dimensional vectors, you know, we might be in a situation where we can't actually draw a linear hyperplane. We might not be able to draw a line that separates these two, okay? However, if we transform it, okay, using some arbitrary phi function, okay, so in this case, if we transform them into 3D, okay, we might be able to draw some kind of linear hyperplane that does separate them. And effectively, our quadratic programming problem is exactly the same. It's in the same form, it's just instead of working with x directly, now we're going to be using this kernel function. So here's a little video, it's a little animation showing what we're trying to do. So here is, we've got red dots on the outside and blue dots on the inside. And if we just did the maximum margin classifier, there's no straight line that you can draw to separate these two things, okay? So what we do is we want to transform this into 3D or some higher dimensional space, okay? So here, if we apply the transformation of basically I think this is the transformation where we have x1, x2, and then x1 squared plus x2 squared. So basically we're keeping the x1 coordinate the same, the x2 coordinates the same, but we're adding a third dimension, basically where values near the origin don't, don't go up much, but then values far away from the origin, get spaced out higher, okay? So now there's a third dimension, and with this third dimension, now we can draw a linear hyperplane that will separate the blue dots from the red dots, okay? So we have this, we can draw this hyperplane, and this will form the boundary that separates our two classes here. Okay, so that so that's what's going on. Okay, now we don't actually, because we're using the kernel function, we don't actually need to take our data and transform it. I mean, like we could, all right? We could if we wanted to and say, hey, this is the transformation function. I'm going to take, here's my data, it's in 2D, we're going to transform it, so now it's in 3D, and then we will use our maximum margin classifier. We could do that. But by just using the kernel function directly, I can kind of keep everything in the same form here. And if I apply the quadratic programming to figure out what is the optimal solution for this, it's going to effectively be working in that higher dimensional space. Okay, so that works. Okay, and you have a whole bunch of different possible kernel functions. Okay, so you have a Wikipedia article of a bunch of these different positive definite kernels that exist, okay? And I don't know, so the linear kernel doesn't do anything, but then you have these polynomial kernels, and then one of these that's very popular is the RBF, the radial basis function, or the Gaussian kernel, okay? And this takes this thing and applies this transformation, okay? Now, the crazy thing is that this, the radial basis function kernel, its corresponding transformation function actually transforms it into a vector of infinite length, okay? So here was a simple function that went from 2D into 3D, okay? But if you use the radial basis function kernel, its corresponding transformation function technically goes from 2D into infinite D, okay, infinite dimensions. And it's based on the Taylor expansion of the exponential function, right? So that's a famous expansion that technically goes on to infinity. Usually you just stop after the first 4 terms or something, but technically it goes to infinity. And the thing is you don't actually need to transform those vectors directly. You can just use the kernel function directly and get the same kind of results. And so, so this is the radial basis function, and within the radial basis function you have this parameter sigma, okay, or sometimes it's called gamma, which is going to affect kind of the properties of the boundary that gets drawn. Okay, so here's some just arbitrary data. This comes from Elements of Statistical Learning, and let's say we want to draw something that's going to separate, red from black. And so here I'm going to just use SVM, and I'll just show you the linear kernel at first, and it's trying to do its best, and it says if you had to draw a straight line to separate red from black, this is what we would end up drawing, okay? And here it gives us these parallel hyperplanes, and again we have kind of a soft kernel or a soft margin that allows for things to end up in the margin and things to end up on the wrong side, okay? Otherwise we would say there's no solution that works, okay? With a polynomial kernel, you can bring in a few additional parameters, okay? So as far as the polynomial kernel goes, there you can have change the C and the D, and basically, as a kernel, the K corresponds to an inner product of this feature space to some mapping. And so anyway, basically, you have all of this stuff here. And so this is kind of it's best trying to do with a degree 3 polynomial. It doesn't do a great job. You can increase the polynomial degree, and I don't know, this doesn't look that great, but here it is, a degree 5 polynomial. In my opinion, not doing a great job here, okay? And again, here I also put in additional kind of, like, once you draw this boundary, like, here's a bunch of additional dots that get colored in, okay? Meanwhile, probably the most popular as far as support vector machines is to use this RBF or Gaussian kernel, okay? And so here I'm going to say the kernel is radial, and then you have these two parameters, the gamma and the cost, okay? And so we'll just explore some of the effects of changing these things, okay? So the cost is going to be basically, it's kind of like that soft margin, and it's going to say, it's asking, like, how bad is it to have a point that is misclassified, okay? And so the cost is going to be basically how much influence any one dot can have on the line, okay? So remember, I don't know, several slides back, we said by using this soft margin, we're putting an upper bound on what how much influence any one point can have, okay, on determining this boundary. And so with a high cost, we're going to be saying that one point can have a lot of influence, okay? The gamma factor here is going to affect basically how flexible our boundary can be drawn. So, I don't know, I would say the gamma is kind of like, are you using a fat cable to draw, like, to separate it, right? And so if you have like this big fat cable, it's really hard to get like tight curves and turns, okay? You have something smaller, it's easier to get tighter curves. You have like a really thin cable here, right? Like you can, do like little, flexible twists and turns there, right? So I like to think of gamma like having a small gamma is like having a big fat cable or hose that's hard to make tight turns in, and a small gamma, or I mean a large gamma corresponds to having a very thin, very flexible wire, okay? And then the cost is going to be how much influence any one point has on the thing. So both of them, like if you increase your cost really high, then you're going to tend towards a high variance, okay? If you have gamma really high, you'll have high variance, okay? If you turn gamma really low, then you'll have less variance but higher bias, okay? Same thing with the cost, less variance but higher bias. So this is just one kind of like a starting thing there. And then here, so I'm going to just show you what happens. Here I've got gamma. I'm going to keep the cost set to 1, Okay, this is going to be how much influence any one point can have, but I'm going to alter gamma from 0.1, which is kind of our least flexible, to here's gamma 0.3, and you can see kind of the boundary there is the thick line, and then kind of our parallel hyperplanes. So again, imagine in the higher dimensional space, you're drawing these parallel planes, and then when they get projected down, you get, these are what the parallel hyperplanes look like, okay? So here it is, gamma 0.3. I'm going to increase the gamma even more. You can see the turns get tighter. Gamma 1, okay? And so this seems to be doing an okay job of separating the red from black, okay? Gamma 2, now our turns get even tighter, and it's trying to accommodate this set of points out there. And with gamma equal to 5, okay, it's really trying to kind of draw tight boundaries that it wants to accommodate that, but it also wants to make sure we're classifying these ones correctly. It even starts to try to draw a circle over there, okay? With gamma 10, yeah, we get, now we're getting a whole bunch of kind of exclaves and, really, really tight twists and turns there, okay? And this is all with the same cost of 1. Here, I'm going to keep gamma locked in at 0.5, okay, which will kind of keep things at a certain amount of flexibility, but we're going to change how much any one point can influence the boundary, okay? So keeping gamma, so keeping kind of the overall boundary there, we're going to say, all right, some of the points can influence and push the boundary around a little bit more, okay? Here's cost 1, cost 2, cost 5, and cost 10, okay? So we can see, if you pay attention to these dots out here, okay, we can see, all right, these red dots, they were not really able to kind of push the boundary around that much. As I increase the cost, though, these red dots are now starting to kind of show their influence on the boundary. And as I increase the cost, which is basically how much any one dot can influence it, we can start to see that these black dots start to influence the boundary again, okay? Here, we're going to do the same kind of thing, but now gamma is 2, so this is a little bit more flexible to start off with, okay? So this model is a little bit more flexible to start off with, and we're going to just start increasing the cost here. And so by the time I get it to cost equal to 10, we can see these dots really kind of try to influence the thing there, okay? And here it is with gamma equal to 5 and increasing the cost. So now you get, with gamma 5, you have, kind of these very flexible boundaries, so you get these tight turns and whatnot, and with cost high, it's like each point is really trying to influence where these things go, right? So here's cost, gamma 5 cost 10, gamma 2 costs 10, and gamma 0.5 costs 10, okay? Whereas you can also kind of just see like the different effects of the gamma, keeping the cost the same. The lines get, just a lot more flexible and wiggly there, okay? So these are just some of the different effects of using, of changing these kind of hyperparameters of the support vector machine, which is, again, it's a popular method for classification. And again, really only works when you have two classes separating kind of your positive class from your negative class. But because it is so flexible, there's popularity, and it's kind of comes down to, here we have two parameters to kind of mess around with. You might do some kind of optimization search with cross-validation to try to figure out what's the optimal combination of parameters to do. Unfortunately, with using something like the Gaussian kernel or the radial basis function here, we can't picture exactly what is happening, okay? So it does still feel very kind of mystery black box as far as like, oh, why is it drawing a boundary there, okay? And it's just kind of existing in this high dimensional, infinite dimensional space, and we're drawing some kind of hyperplane there. So that is kind of the drawback, you know, and it kind of just gets pushed out with its predictive performance as far as how well is it predicting future classes. This one's probably overfitting. I'd probably go with something. This looks reasonable to me. And it really comes down to, do I want to have a special carve out for here or not, right? And because this also seems halfway reasonable. So, you know, probably your own kind of judgment, you know, as far as like, this is just fictional data, so I have no idea what x1 and x2 are. And so, you know, the question is, based on your kind of understanding of the domain and whatnot, does it make sense to kind of have a special carve out for some of these points out here or whatnot? You know, this is generally the red zone. This is generally black. That seems to be in agreement across all models. And the question is really comes down to some of these points out here where it does seem like maybe something's going on, or maybe these are just outliers. So, okay. Yeah, that's all I've got for today. So we'll finish again a little bit early. Hope that's all right. Have a great weekend. It's Labor Day weekend, so but I mean, we don't meet on Mondays anyway, so we'll see you back on Tuesday then. Oh, I didn't give you any answers, huh? I just gave you one. Oh man. Okay. Three answers then. Okay. B, A, and A. So B, A. B as in bear, and then A and A. Okay. All right. Thank you.